Aviation fuels from lipids via hydrotreating. The aviation industry is rapidly growing and is a big part of modern life. According to the National Renewable Energy Institute in an article about aviation fuel, fuel is the #1 operating cost in this industry. With about 1.5 to 1.7 billion barrels of jet fuel being used worldwide per year, and there being a depletion of non-renewable sources for this fuel, a lot of time and research has gone into an alternative. Since the first commercial flight powered by biofuel in 2008, there has been a boom in research into bio-based alternatives for aviation fuel. There have already been 5 different fuels approved since 2009 to be mixed with petroleum-based fuel from amounts ranging from 10% to 50% for use in commercial aviation. These fuels have many different raw starting materials, including renewable biomass, waste fats, sugars, and agricultural waste products. However, these products still have a long way to go. The production of aviation fuels is essential for air travel. Aviation vehicles cannot run on electricity. It just doesn't have the capacity to provide the needed outputs to run air transport machinery. Therefore, this sector of the transportation industry requires a dense liquid fuel. The idea of an aviation fuel made from lipids is to displace or completely replace petroleum-based fuel with not having to make any altercation to current engines. Petroleum-based aviation fuels have many negatives, the biggest being their environmental impact. From use, they release significant amounts of carbon into the atmosphere. From extraction of the raw materials, they create even more carbon emission, but also leave hazardous scars both physically and chemically to the surrounding environment. If no improvements are made, in just 15 years, the amount of carbon in the atmosphere from emissions will be more than double in magnitude. On the other hand, bio-based aviation fuel, especially from lipids, has the potential for lower cost raw materials as well as a much smaller carbon footprint, making it the better option. However, this process is still more expensive than petroleum-based fuels and still has a long way to go. This is the motivation for this project. The first step for any project is to well define the problems and questions that need answering. The main question that needs answering is how can a quality aviation biofuel be synthesized through hydrotreating lipids to compete with traditional petroleum-based aviation fuels? This leads to some more specific follow-up questions. What processes already exist? How can these processes be upscaled for commercial production? What is the best feedstock to use? For cost, for the environment, and for a given feedstock, what are the best operating conditions and catalysts that give the highest yield percentages? We use these questions to guide us throughout the project and development for aviation fuels from lipids via hydrotreating.
So by far the largest hurdle that the bioaviation fuel industry faces, and frankly, the biggest wall that is preventing the global adoption of biofuels is its significant production price. Per ton, bioaviation fuel nearly doubles the cost of petroleum-based aviation fuels per ton. And especially with how quick global aviation is increasing and how large and how quick fuel demand is increasing, if we really expect biofuels to completely replace fossil-derived fuels, a reduction in price is needed. It won't be able to compete with fossil fuels currently. Now, one of the ways we can reduce cost of production of biofuels is to just simply scale up production. The larger the production, the lower the operating cost per amount of fuel made. The problem with this is the feedstock industry and distribution chain isn't well adapted to handle large production loads. Essentially, the production is outpacing the supply, and especially with demand and competition with other industries such as the biodiesel industry, prices are further skyrocketed. A solution to this is just to use more feedstocks. Now, this doesn't directly reduce the price of feedstocks in the market, but it does dissipate demand over multiple industries, reduce competition, which inadvertently would reduce the price. Now, to use multiple feedstocks, you have to have a very flexible catalyst, and that is exactly what we use and what we designed our process around. So there are multiple chemical pathways that can produce biofuels from biomass. One of these pathways is hydroprocessing. Now, hydroprocessing is in fact one of the more desirable and has the most potential to dominate the industry because of how similar it is to current fuel production plants. The chemistry itself is very similar. In fact, hydrocracking, which is used in this hydroprocessing of biofuels, is used in the production of fossil-derived fuels. So plants can be modified and upgraded to accommodate for biofuel production. Now, there are two classifications of hydroprocessing: hydrotreating and hydrocracking. Hydrotreating, a less severe reaction environment than hydrocracking. Hydrotreating removes contaminants such as oxygen, nitrogen, sulfur, separates the triglyceride into three individual glycerides. At this point, the process, majority of it will be diesel, about 90%. Then this diesel grade hydrocarbons are then fed into the hydrocracking reactor, which splits the long chain carbon into kerosene grade hydrocarbons, C9 to about C15. Now, this process is very energetic and exothermal, and is the more extreme, has the more extreme optimum conditions, reactor conditions, that being 350 to 450 degrees Celsius and 40 to 110 bar. So both the feedstock and the catalyst have the greatest potential at achieving a significant price reduction in the production of biofuels. Now, the feedstock contributes about, just by itself, 70 to 80% of the overall production costs. The feedstock needs to be able to produce high levels of aviation grade kerosene while maintaining and even improving its competitiveness with fossil derived fuels. Now, there are numerous feedstocks out there that have significant diesel and kerosene yields, but the desired reduction in price cannot be achieved with a single feedstock. Multiple feedstocks are needed. This allows the demand for those feedstocks to be spread out over multiple industries. It allows the competition to be reduced, reducing prices further. And it also allows for a reduction in land usage to grow these feedstocks. Now, the triglyceride oils that we used were sunflower, soybean, and palm oil, all of which have extremely similar operating conditions, yields, and use the same catalyst. And more importantly, they have similar operating conditions and yields while using the same catalyst. Now, the catalyst we chose needed to have great stability, lifespan, regeneration ability, and yield potential. Now, to even get on this list, stability, lifespan, and regenerability needed to be great. Spending too much on the catalyst would further reduce the production or increase the production costs. Now, for the hydrotreatment reaction, we focused more on potential yield because we needed a high product stream out of the first reactor to achieve a high product stream out of the second reactor. Now, we chose a nickel molybdenum catalyst over a non-acidic base. Now, this operated at 350 degrees Celsius and 50 degree bar in Aspen, and it essentially is a catalyst that allows us to use multiple feedstocks. It is feedstock flexible. Now, for the hydrocracking, we used a nickel molybdenum catalyst over an acidic base. This acidic base allows for the cracking of the diesel molecules. Now this kerosene or this catalyst needed to be able to be stable at high temperatures. And it also needed to be able to produce respectable amounts of kerosene. Now this reactor with this catalyst was operated and modeled at 410 degrees Celsius and 40-degree bar. So here's the overview of our process. There are four main units in order. They are the hydrotreating reactor, the distillation column, which will separate the product stream from the hydrotreating reactor from any lighter carbons that are unneeded, the hydrocracking reactor, which will crack the incoming diesel from the hydrotreatment reactor into lower grade hydrocarbons such as kerosene, hopefully producing 50 to 55% kerosene, with some naphtha and propane also being produced, which are then separated out in the second distillation column with a close to pure diesel stream, diesel outlet, kerosene, naphtha, and lighter carbons. Now it's important to note that we have two hydrogen feeds in this reactor, and that's because both hydrotreatment and hydrocracking are hydrogen dependent. They consume a significant amount, enough to where reducing the consumption of H2O will significantly decrease the price of production of aviation fuels. So here's a simplified version of our Aspen model, only representing the major units that were used. We have the mixer, the furnace, the reactor, the separator, and then the distillation columns for the hydrotreatment and hydrocracking. Now it's important to point out that there are two additional distillation columns. That is because to achieve the necessary purities in the product streams, distillation columns operated in series was required, especially after hydrocracking. The product stream was composed of significant portions of diesel, kerosene, naphtha, and lighter hydrocarbons. Now the first distillation column separates the diesel from the kerosene, and then that distillate is fed into a second distillation column where it separates the kerosene from the naphtha and potentially lighter hydrocarbons.
The sections of our process mentioned in the preceding slides are generalized and simplified on this slide here. As you can see, the feedstock section pertains specifically to triylene due to it being an ideal triglyceride with zero impurities and a single saturated bond. Both the hydrotreating and hydrocracking reactors discussed previously were modeled with R stoics and were used to contain all reactions and get any potential yield values. Additionally, we have the separator, which is intended to select byproducts and excess reactants separated from hydrocarbons. We also have two distillation columns in which the first distillation column is used to separate the light and heavy hydrocarbons, while the second is used to separate kerosene and unreacted diesel.
In conclusion, some of our questions were answered and some are still in the process of getting answered. We concluded that the two-step reaction process is the best for both cost and yield. It allows each step to have a dedicated catalyst, which is projected to improve both the yield of diesel and kerosene in addition to plant efficiency. The introduction of this flexible catalyst also allows for more than one feedstock to be used at the same time. The benefit of this is increased plant efficiency and the decrease of demand and market competition with other industries, causing a reduction of feedstock prices and a more competitive selling prices.
This project still has some work that needs to be done. A more rigorous economic analysis is needed to better understand how much operating the process and purchasing raw materials will cost. A life cycle analysis is also needed to better understand when the process needs to be shut down for cleaning and when the catalysts need to be cleaned or replaced, as well as how the quality of the end product, kerosene, will be affected by long-term production. The most important thing that still needs to be done is improving the model. This means adding a catalyst to the system and using a less ideal, more realistic, starting feedstock to better understand the needs of the process. This also includes better utilization of excess reactants and byproducts. This includes separating out excess hydrogen for recycle back into the feed stream and the recycle of uncracked diesel back into the cracking reactor. Once these are done, more improvements can be made to decrease the cost of production and increase the yield percentages.